Hello my beautiful students. So today I'm here for a new session. I'm your new chemistry teacher, myself Sayani Mam. So just a little bit about myself. Though Aishwarya Mam has introduced me on last Sunday, actually I have done my master's degree from IIT Kharagpur. I'm pursuing my PhD right now from ISC Bangalore, as well as parallelly doing the B.Ed course. And the most important and the beautiful thing is I'm teaching you people as well. And this is going to be my first ever video in this particular channel. So I'm really very much excited to pursue a new journey with you people. So if I move towards today's topic, so we are going to proceed with the model paper, and I know it's a very demanding video that you people really want. You people kept commenting on this particular thing, and now finally this is the day and we are going to start with the PU2 Chemistry Model Paper. And just one more suggestion I want to tell before starting the video. You're preparing very nice, I know, but just to spice up the things, I just want to make you practice a little bit of these along with some concepts connecting to the particular questions, so that you can connect the concepts and you can solve the papers simultaneously. I guess this will help you in the better preparation. So without any further delay, let's proceed for our today's topic. So before going towards the section A questions and all, I know you are very much in rush whenever you will get to see the paper. You are very much in rush. Such an easy question, we can do it nicely. But we must be assured that we are pursuing and we are going through this particular portion very consciously, because this particular portion, how much marks each question carries, how many questions you have to attempt, it plays a really crucial role whenever you are going to write the examination. And also the time management, it's another big deal that is kind of related to this particular thing. So let's proceed a little bit. So first thing that you are going to start with part A, that carries 20 marks. In this particular case, you will be having 15 marks, that is MCQ, and 5 marks you will get fill in the blanks. Next you will see this is the part B. It actually carries total 6 marks, and you will be having 3 questions over here, and you have to write them. And next it comes part C. It carries actually 15 marks, where each question carries 3 marks. Here comes part D, that carries 20 marks, and each question carries 5 marks. And finally the part E, that carries 9 marks, and each question carries 3 marks over here. So let's proceed. So here comes a better representation of what I said in the last slide. So you can see the question 1 to 15, you are going to face the MCQ. This is a 1 marker question. Question 16 to 20, this is a fill in the blanks question. That is also 1 marker. 5 questions you are getting out of it. Question 21 to 24, you are getting 2 marks question, and 5 question you will get out of it. 5 question you will get out of it, and among which you have to write 3. Okay. Next we will proceed with the 26 to 34, question number 26 to 34. Here basically you are going to face total 9 questions, but you have to choose 5 questions among them. So how these 5 questions? These 5 questions, by analyzing, I got to know 3 you are going to face from the inorganic, and 2 questions you are going to face from physical. So total 5 questions out of this 9. I guess you understood this. Next question 35 to 40. This is the long answer type question, and here also you can see it's got total 6 question you will be having, but you have to write the 4 out of it. And the last one 41 to 46, you will be facing numerical problems, and in the numerical problems you can see you will be having total 6 question, and 3 you have to do among them. So without further delay, let's proceed for the. So yes guys, let's proceed with the first MCQ question. So let me just tell you, while discussing about these questions, I will be keep connecting you with the concepts as well. It's not just a random question answer solving series, rather you are going to connect yourself how much you have clarity on the concepts. So let's first start with the first question of the series. So the mass percentage, that is W by W, of glucose in water is 10%, means you have 4 options. 10 gram of glucose dissolved in 100 gram of water, 10 gram of glucose dissolved in 90 ml of water, 10 gram of glucose dissolved in 100 ml of water, 10 gram of glucose dissolved in 90 gram of water. So before proceeding with this particular thing, let me just give you a small concept about the mass percentage. Let me just make it a little lighter for you so that you can understand. So mass percentage. Okay, so mass percentage we sometimes refer in the form of W by W, right? So whenever you are just doing it, we simply apply a formula, that is mass of the solute divided by total mass of the solution. So as you can see, just by looking at the formula you can guess, just by looking at the formula you can guess that in the numerator also it is gram and in the denominator also it is gram. So there is no chance to write it in the unit of ml. So by default this and this getting cancelled, because they are saying about 90 ml of water and 100 ml of water. So it's getting cancelled, right? So now let's see, first option is 10 gram of glucose dissolved in 100 gram of water and another one is 90 gram of water. So 90 gram, if you just look at that, it is the only amount of solvent, right? But you can see I need the total mass of the solution. So total mass, if you just calculate, it will come in 100 gram, because you are doing it in percentage. Percentage means we know it is how much in 100, right? How much in 100. So definitely the answer is going to be 10 gram of glucose dissolved in 100 gram of water. So I guess you got better clarification and you could recall how I connect the actual concept with this particular MCQ. So let's proceed for the next one. So here this question is quite easy. Achha, let me do one thing for you. Let me mark if the question is of easy level or moderate level or a little bit tricky or difficult level, or you need to do some tricks over here, you need to know some numerical knowledge or something like that. Let me just mention those things for you as well, so that it will be really I guess helpful for you to understand the level of the questions. Let's proceed. So for this it is a kind of easy question, you can say. Let's proceed further. This question, which of the following elements is liquid as at normal temperature? First one is zinc, mercury, aluminium and water. I guess you know this better than me. You have a proper idea about it since class 10th. So definitely you guessed it correctly. It is mercury. So definitely it's going to be a super easy question. So next one, let's proceed. Next one. The reagent used in Sandmeyer's reaction is, first option nitrogen gas, option B Cu and HCl, option C Cu2Cl2 and HCl, option D CuCl2. So before dealing directly to the reagent, let's at first deal with the reaction itself. So what is Sandmeyer's reaction? So let me just start with the aniline. So this is your aniline. So if aniline is treated with NaNO2 plus HCl, and if you maintain the temperature from 0 to 5 degrees Celsius, sometimes you can see people are writing together HNO2. because if NaNO2 reacts with HCl, it will definitely from HNO2, so both of them are okay. Fine. So if aniline reacts with these species, it will form that famous element What is the name of this compound? Yes, if you guessed it, very nice. It is benzene diazonium chloride. So once you are having this benzene diazonium chloride, then just add Cu2Cl2 plus HCl. This entire N2Cl minus group will be gone, and that particular portion will be replaced by chlorine. So similar thing, if you just add here Cu2, Br2 and HCl, if you proceed with this, then also you will be ending up with the substitution of Br. This particular portion, this reaction is basically the Sandmeyer's reaction, So here one most important thing that I must tell you, they sometimes in the question they play with the copper compound, copper salt better to say. You can see it is CuCl2 and here also you can see it is Cu2Cl2. But one major difference is there, the oxidation state of copper. So what is the oxidation state of copper? Oxidation state of copper in the Sandmeyer reaction must be +1. If you just calculate here what is the oxidation state of copper, you will see it's basically +1. So be careful, whatever the copper compound they are giving, please be assured that the oxidation state of copper must be +1 here. But here if you see, here the copper is +2. So definitely that's not going to be the answer. So for your further reference, just I have kept one slide so that you can get a better clarification, and definitely that nitrogen gas will be eliminated from the system. Right? I guess you understood this question, so definitely your answer is going to be this one. So let's proceed further. The main natural source of acetic acid, the first one is milk, vinegar, red ant and butter. I guess you know this better than me, so definitely it is vinegar. Okay, so let me just mark it. It's a super duper easy question. And what about the last one? You can just call it a moderate level question, because if you know it, then it's super easy. If you don't know it, you can't answer it. It's like that. So let me just mark it as a moderate one. So let's proceed further. Okay. So the reaction of aniline which produces Zwitter ion as a major product. So let me just give you a little bit idea about what is Zwitter ion. So basically this Zwitter ionic form majorly we see in protein. Right? So there you can see the charge separated version, C double bond O minus, and another end you will see NH3 plus. So it's a dipolar compound. In a single compound, here you are having plus charge, here you are having negative charge. Okay, these particular charge separated version, not necessarily it always must be an amino acid. Just like you can see here in the aniline, whenever you are just proceeding with the reaction with some sort of reaction, it will proceed with, it will give you Zwitter ion. That Zwitter ion you will see it is a charge separated version with NH3 plus and another negative counterpart. So let me tell you what is the answer basically. If you do direct nitration, so one nitro group will be added simply. Right? One simple nitro group will be added. So there is no chance of having a charge separated version. Why? Whenever you are proceeding with the Zwitter ionic conformer in a single compound, you must have some basic unit, and in a single compound you must have some acidic unit. Let's just take some example of amino acid. If you just look at amino acid, one end you are having NH2. That NH2 part is basic, lone pair donor. Another part, if you just look at that, that is COOH. That is acid donor, H plus donor. right? So one part is basic, another part is acidic, right? So same type of thing I need here as well, right? So nitration will not help me in this particular regard. So if you just make it bromine, no, NH2 part is, I know it's basic, but bromine will not help me by giving some acidic portion. No, it will not help. Let's do sulfonation. Yeah, it has a chance. So further, if you just proceed with the sulfonation of aniline group, this is your NH2, and if I further proceed with some dilute H2SO4, then you will be ending up with something like NH2 and here SO3H, right? This particular thing is in equilibrium with its Zwitter ionic form. That is, you can see this is the acidic hydrogen, right? So this acidic hydrogen will be taken by this basic part. So if it takes up, it will form NH3 plus, and here you will see SO3 minus, right? This particular thing is Zwitter ion, right? So sulfonation of aniline is going to give me Zwitter ion. Let's proceed. This is the overall reaction. I just gave an overview of this reaction. You can see first just simple diluted acid you just give. At first initially it will form NH3 plus HSO4 minus, then just a little heat and it will rearrange to give you this particular thing, sulfonilic acid, and further it will be in equilibrium with these Zwitter ion. That's a dipolar ion, you all know this. I guess the conceptual clarity you got, and as well as you got to know the answer. So if you ask me to mark, it is a little difficult level question. If you know this, you can do it. Let's proceed further. Okay, so next question, you can see the method used to separation of isomeric products obtained when phenol reacts with dilute HNO3 at low temperature. So at first, let's see what this phenol will make once it will react with dilute HNO3. Let's proceed. So this is my phenol. So if it reacts with dilute HNO3, I will get the mixture of orthonitrophenol, and I will get the mixture of, and I will get another compound, that is the paranitrophenol. Okay, very nice. Now how I should separate them, right? So first, if you just look at this particular compound, if you just look at this first one, the ortho compound, this particular compound is having high melting point. Sorry, this particular compound is having low melting point and it's highly volatile. Why this is so? Why this is so? Because it forms intramolecular hydrogen bond. It forms intramolecular hydrogen bond, and you can see one 6-membered stable ring is formed because of the intramolecular hydrogen bonding. As a result of this, it don't get assembled with other orthonitrophenol present in the same reaction media, right? So that's why this compound is highly volatile. So definitely just with a small temperature, with a little heat, you can isolate this. But while looking towards this compound, this is paranitrophenol, it is also having the hydrogen bonding, but that is with another molecule of it. So like that it will be continued. right? So for this particular case, you are having intermolecular hydrogen bonding. And hence you need more energy to break this interaction and to make it separated, right? And it is having high boiling point. Melting point, let's write high melting point, right? So once there is a huge difference in the melting point and boiling point, you know which separation technique we use. So definitely if you have guessed, it's definitely correct. It's basically the steam distillation. I guess why steam distillation, that reason also you understood in a better way. Let's proceed further. Here comes the next question, that is a ligand which forms more stable coordination complexes is, and there comes 4 ligands, ammonia, C2O42 minus and H2O. So for this particular case, let me just tell you some concept of ligand field theory is actually attached to it. You have to know which one is the strong ligand here, and if I just tell you, if I just clarify a little, Cn minus is the strongest one, and after that if you proceed, ammonia will come, and after that water. Now the question is with this one, oxalate. So C2O42 minus, that is the oxalate one. If I just better draw the structure, it has 2 donor site, right? It's a bidentate ligand. It's a bidentate ligand. So definitely you can tell me that whenever it's a bidentate ligand, it chelates the particular metal in a better way. So it should be the strongest one. But this chelation also depends on another factor, that is what metal is provided to you. And nothing is clear in this question. What metal or what is the complex, nothing is clear. So whenever it comes to a generalized version, that is what is a more stable coordination complexes, we will proceed with the ligand strength, and in order to this, Cn minus is having the maximum strength and it can form the more stable compound. So definitely this option C is going to be the correct answer. So this is a moderate type question, you can tell. Okay, so let's proceed further. Okay, which of the following groups when present at para position increases the basic strength of aniline? Fine. So this is my aniline, right? Now let me tell you why aniline is basic. Aniline by default it's basic. So by adding any one of this group can increase the basic strength of this aniline. That's a secondary matter. Let's first understand why this aniline is basic itself. Aniline is basic because of the presence of its lone pair, right? It donates its lone pair. Nitrogen has its own lone pair, it donates its lone pair, right? More the donating capacity, more it will be basic, right? Now just let me tell you a very realistic phenomenon. Let's say I also want to donate and you also want to donate, right? So I am also having some sort of money, you are also having some sort of money. Very good, we are about to donate, but there is a problem. What problem? Whatever the money I am having, it's there in the fixed deposit. I can't use it. It's there in the bank. But whatever the money you are having liquid cash. So whenever you want, you can donate, right? So always be assured, maybe I am having money, maybe I am having this lone pair to be donated, but those lone pair must be available for the donation. Now let's just expand it in a bigger aspect. You are ready to donate, but there are something that is stopping you from the donation. Rather, someone is taking away your money. Someone is there to take away your money. So how will you donate? So the same thing will happen here with the aniline as well. So I have to see who is that person who is taking money from you. Let's see, if you are having NO2 group, let's analyze what kind of electronic displacement effect these particular groups are showing. So first of all, this NO2 group is electron withdrawing. Electron withdrawing group, and indirectly you can say that they are having minus R or minus M, means the mesomeric effect it is having minus, because it is taking away the electron, right? For bromine, it is basically electron donating group. Sorry, if you just discuss about the bromine, it's basically electron withdrawing group. Okay, so let's proceed with the next question. So, which of the following groups when present at the para position increases the basic strength of aniline? So, at first let's understand this particular aniline, why it is basic, what makes it basic. Then we will see which group, how they are enhancing the basic strength of aniline. Nitrogen of aniline has its lone pair. So these lone pairs made it basic. How? Because it's a lone pair donor. So once it is a lone pair donor, we call it a base, right? Now, just let me come to a very realistic example. Let me connect you people to the reality. How? So, let's say I am also having money, I want to donate, and you are also having, you also want to donate. Fine. Now, whatever the money I am having, it's there in the bank in the format of fixed deposit. I can't break it. I can't get the liquid money out of it. But whatever the money you are having, that is in the form of liquid cash. So whenever you want, you can donate, but I can't donate it. So availability of the money is one of the major fact that you have to emphasize on, right? So here also you have to take a look on the lone pair, and you have to think if the lone pair is available for the donation or not, right? Now let's say you are having money, you are ready to donate, but someone is there who is taking away your money. Then how will you donate? It's not possible, right? But if someone is there, who can give you more money, let's donate together. Someone is there to donate you more money, right? In this case, you will be having more money, right, to donate further, right? So if someone donates, if someone gives you money, you will be having more money and you can donate it. So the same thing we will see here as well. We will see who is taking or who is snatching the electron from the nitrogen and who is giving the electron to the nitrogen for the further donation. Let's proceed. So here you are having NO2 group. So NO2 group is electron withdrawing group. It takes away the electron. And indirectly, if you ask what effect, you studied electronic displacement effect, right? So if you connect that, it is having minus M or minus R. Minus M, I guess you know, it's a mesomeric effect. Minus M effect, it can take away the electron withdrawing group. If you just look at the bromine for the next option, it is also electron withdrawing group, right? So whenever it is an electron withdrawing group, so it withdraws the electron with its minus I effect. Minus I guess you know, it pulls the electron cloud towards itself. Got it? Next, let's proceed. NH2. See, again NH2. Again lone pair. So it is having excess lone pair, so it will donate. So it is electron donating group with plus M and, or you can say plus R effect, right? Next, COOH. Again, it's an electron withdrawing group with the same minus M effect. Right? So now I guess you got a clue what is the answer. So definitely it's electron donating group, that is NH2. If it is present here, then it can donate more electron to this particular nitrogen, and these lone pairs will be eligible for the further donation, and hence basic strength will be increasing. I guess proper clarification you got. Let's proceed for the next question. In the following acid, vitamin is first one ascorbic acid, adipic acid, aspartic acid and saccharic acid. This is a very easy question. So if you wanna just let me tell, it's a super duper easy question and the answer is going to be the ascorbic acid. I guess you know this. And last question, if I just go back to the last question, then this, it's a moderate level question. Okay, let's proceed further. Okay, the best reagent useful for the separation and purification of aldehyde from ketone. So this is a particular portion of NCERT. That is a very important zone. Actually, I will show you that portion from where this thing is taken out. So let me just tell you, the answer is going to be sodium hydrogen sulfite. Okay, why? Let's say I'm having one carbonyl. Okay, I'm having one carbonyl. So I'm having NaHSO3 along with this. So once I'm having NaHSO3 along with this, so this will definitely react. It's an addition reaction and equilibrium exists in between them, and it will form some compound like this. And after doing some proton transfer, it will form something like this. This particular thing, right? Now if you give some let's say dilute mineral acid, it will give you back the carbonyl compound. Okay, now if you identify which particular product, means in case if I am starting with aldehyde or in case if I am starting with the ketone, which particular case I'll be having more product, then I can tell that is the best, right? Now let me tell you, if it is an aldehyde, it is something, one side must be H, another side must be R, right? It's an aldehyde, right? So in case of aldehyde, this addition product, if it is a mixture of aldehyde and ketone, this addition product will be more for the aldehyde, lesser for the ketone, means ketone will be in that side. What is the reason? The reason is ketone is having more steric hindrance, right? Because with the carbonyl you are having both RR group, right? So someone is going to be added here, so it is facing more steric hindrance because of the presence of two bulky groups, right? As a result of this, aldehyde will react more and more, and it will proceed forward in this reaction and it will form the product. And if we, this is a water soluble thing, this water soluble thing if we just take out and if we put some dilute mineral acid, then again I will get back my aldehyde, and the ketone will not react that much because of the steric hindrance. Okay, so definitely it's the best reagent for the separation as well as the purification. So let's proceed. Let me just show you from where I just took this portion. This is a book, there's a page from the NCERT it's taken. So you can just pause your screen and you just can go through this portion. I guess the concept will be clear to you. I guess you are done. So let's proceed for the next one. So here comes one assertion reason type of question, or statement 1, statement 2. You have to just find out the true, false, or let's see, let's proceed further. Statement 1, you can see, if on mixing the two liquids the solution becomes hot, it implies that it shows negative deviation of Raoult's law. Let's see if this particular statement is true or false. We will get to know. See, they are saying I am ending up with a hot solution, right? It means enthalpy of the mixture is negative. The value will come negative because then it is an exothermic reaction. Better to say at first it is an exothermic reaction. And hence from here I can tell enthalpy is negative, or you can say it is basically less than 0, right? It is less than 0. So now I guess you people can connect, if the enthalpy of the mixture is less than 0, it is nothing but the negative deviation of Raoult's law, right? So we can see that statement 1 is definitely true. Let's proceed for the statement 2. Solution which show negative deviation are accompanied by decrease in volume. Let's proceed further. So you can see whenever you are having, let's say, delta V mix, means volume of the mixture, it is negative, right? It increases, decrease in volume, right? It implies as decrease in volume. Why? You know what? Whenever the volume actually decreases, the reason behind it is the interaction between the two component of the solution. Let's say I am having A and B. If I am having A and B, so if the interaction between A and B is so much, then it will arrange themselves in a more compact way, right? It will arrange themselves in a more compact way, and hence we will see the decrease in volume. And when it is possible, when the del V mix is negative, it is definitely whenever the negative deviation of Raoult's law takes place. So I guess it's clear to you. Let's proceed. So it's also a moderate level question. Let's proceed for the next one. This particular thing. Okay. So definitely in your exam you can expect this type of matching type of question. One of the question will be like this. Definitely one of them will be true, false, those type of question you can face. Okay. So here let's see first one by one. Let me do it. So question is, match the following transition metal compounds with their catalyst activity in the corresponding process. Okay. So first one is TiCl4 plus AlCH3 whole thrice. This particular catalyst is called Ziegler-Natta catalyst. Ziegler-Natta catalyst, and this particular catalyst is used for the manufacture of polythene. So definitely one is going to be C, right? Next we will proceed with PdCl2, palladium chloride. So this palladium chloride it's used for the Waker's process. Okay, so this particular thing is for the Waker's process. So here, what is Waker's process? Just a small glance let me give. It is basically used in the conversion of ethene to acetaldehyde or ethanol, whatever you want to say. Okay, for this particular perspective, I need PdCl2, that is a Waker's process. Next comes nickel. So this is my option A. Next comes nickel. So nickel, definitely whenever you will see any one of them, no, nickel, platinum, palladium, this type of metal surface, only the metal is used, then like without thinking twice, just proceed for the hydrogenation. Okay, so it always helps in the hydrogenation. It provides the surface for the hydrogen to get accommodated on the surface in the, and from that particular hydrogen we get some nascent hydrogen that again gets any kind of fat or unsaturation, those particular thing gets reduced. Okay, so for this particular case I am getting option D. Okay, so definitely the last one, V2O5, that is used for the contact process. So let me just tell you what is contact process. Contact process is nothing but the preparation of H2SO4. Okay, it is an catalyst that helps the oxidation process from SO2 to SO3. Okay, so now if you just check with the option, I can see something nice, I can see both A and B is going to be the correct option. Okay, so I guess there is no doubt you could relate the things with your concepts and as well as you could solve the problem. So it is a kind of difficult question because you have to proceed with this many catalysts and you must know in which purpose they are used. Okay, so let's proceed further. Here comes cumin hydroperoxide on hydrolysis of dilute acid gives, the products are given in the option. So for this particular case, let me just tell you, we had been through a very famous reaction, very important for the board as well, cumin to phenol synthesis. Okay, it is definitely there in the phenol, the chapter alcohol, phenols and ether, you will get the reaction over there. There comes a product in between, that is cumin hydroperoxide. So just let me write the product for you people. It is something like this. So definitely whenever peroxide term comes, just this type of O single bond O linkage is mandatory. This is your cumin hydroperoxide. So if it undergoes hydrolysis in presence of dilute HCl and a little bit warm up, you will end up definitely with phenol. Along with that, you will end up with acetone. So as you can see, your option is going to be D. So this is also a moderate level question. I guess there is no doubt. Let's proceed for the next one. This case, among the following cells, the cell used in Apollo space program for providing electric power. So it's a direct question from the lines of NCERT. So this is a very super easy type of question, and if you guessed, it's really very easy. It's H2O2 fuel cell. For your further interest, I added one photo of this particular fuel cell that was used by that time, just for your further interest. Anyway, let's proceed for the next one. Oh, this particular thing definitely I can see. By judging the question, I can understand it's from the kinetics and it's related to the rate law. Let's proceed with the question. The following results have been obtained during kinetic studies of the reaction A plus 2V gives C. Choose the correct option for the rate equation for the above reaction. Okay, so here comes the data. What kind of data I'm having? So whenever I'm having experiment 1, I kept the concentration of A as 0.1 and the concentration of B as 0.1, and I'm calculating the rate, I'm getting it like that. So this is how I have conducted 4 sets of experiments, right? And I got the rate value like this. So now I have to tell what's going to be the rate equation for this particular reaction. One mandatory thing that I must tell, they did not tell it's an elementary reaction. So please don't consider this stoichiometry as the order of the reaction, because we know in case of only elementary reaction, the stoichiometries are considered to be the order of the reaction, but the rest of the cases the order is an experimental value. So thus the experiment has been conducted and we have to find the rate. So let's proceed. So how, in case you are just dealing with this type of problem, just let me just tell you a process what you can follow. So first, normal you write the rate equation in general, okay? So rate is equals to rate constant into concentration of A. Let's say the reaction is X order with respect to A and Y order with respect to B. So by any means, if I can find out the value of X and Y, I can tell what is the rate equation, right? So now how I should actually find out? Okay, so I am having 4 sets of equation from here. How 4 sets of equation? So one by one, let's write the rate. So rate 1. Okay, so rate 1 is something like concentration of A is something 0.1 power X, B is something 0.1 power Y. So R1 value is, rate value is I am getting 6.0 into 10 power minus 3, right, equals to K into 0.1 power X and 0.1 power Y. Let it be my equation 1. Like that, I will develop the 4 equations corresponding to the data. So this is equation 1. Equation 2 is something like 7.2. This is for R2, right? This is for R2. 7.2 into 10 power minus 2 into 10 power minus 2 will give me K into 0.2 power X and 0.3 power Y. This is my equation 2. Let's proceed with the equation 3. This is rate value something 2.4 into 10 power minus 2 will give me K into 0.1 power X and 0.4 power Y. This is 3, right? Another one, 2.88 into, this was my R3 and finally I am proceeding with the R4. So 2.88 into 10 power minus 1 equals to K into 0.4 power X and 0.3 power Y. So now I am having 4 sets of equation. So whatever I have to do, I have to deal with this 4 equation and I have to find out X and Y value. So how I should proceed further? Let's do something. I am doing R3 divided by let's proceed with R3 divided by R1. So once I am going to do R3 divided by R1, just a minute. Once I am proceeding with R3 divided by R1, in this particular case, what I am going to see, R3 is something like K into 0.1 power x into 0.4 power y divided by k into 0.1 power x and 0.1 power y. So from here you can see this thing gets cancelled out, k gets cancelled out. So let's put the R3 value. So from here R3 is coming from the equation also you can put, it's quite similar. It's coming 2.4 into 10 power minus 2 divided by 6.0 into 10 power minus 3 is going to give you, see, if you just calculate 0.1 and here 0.4, it will give you 4 power y, right? So now if you just simply calculate this thing, it will come as 4. So 4 power 1, nothing is there in the power means it's 1. So 4 power 1 is equals to 4 power y. If you compare from here, I am getting y equals to 1. Right? Another thing, so y value I got. Another thing that I can do is, I can do let's say R4 divided by R2. Okay, let's further proceed. So this is going to be something 2.88 into 10 power minus 1 divided by 7.2 into 10 power minus 2, that is equals to k into 0.1 power x into 0.3 power y divided by k into 0.2 power x into 0.3 power y. So from here 0.3 power y, 0.3 power y, k and k gets cancelled out. So I am getting a very simplified version out of it. Sorry, this is 0.4. Okay, so now if you just calculate these, you will get 4 out of it. So 4 is giving me, if you calculate 0.4 divided by 0.2, you will get 2 power x. So from here I can again compare 2 squared equals to 2 power x. It means x value is 2. So now how we can merge the concept, all together. So definitely from here, just let me write it here below. So rate of the equation is going to be k into a power x, means a power 1, right? Sorry, a power 2, because a power x, b power y, right? So from there a square and b power 1 I am getting, right? Just substitute the value of x and y over there. So definitely by just looking at the answer, you can tell that the answer is going to be C. I guess you understood this. So whenever you will see this type of problem, then just focus on the data and check in which case you can just eliminate at least one term. Like here you can see for the concentration of A, this value is quite similar. We can eliminate. So make the ratio of those particular rates. Okay, for this case intentionally I did it R4 divided by R2, I made the ratio. Okay, why? Because I observed that, okay, concentration of B can be eliminated. So this thing, keeping these things in mind, just eliminate one of the term and you will get the x or y, whatever the value you will get out of it, and then put it into the rate equation. This is how you need to solve this type of problem. So let's proceed for the next one. Okay, so here comes the second half of the section A, that is a fill in the blanks type of question. So you can see it's dealing with this type of things are very easy because you are having options, so you can deal with the most relevant option and you can put it here. Okay, very less chance to make it incorrect, right? So the first one, the polyhalo compound that is used as an aesthetic during the surgery. So there is a printing mistake I guess, it's a anesthetic, it should be anesthetic during the surgery. So definitely if you just look at this, you people know that chloroform is an anesthetic reagent. So it's a polyhalo compound. Why? Because the formula of chloroform is CHCl3. It has 3 chlorine, means 3 halogen, right? So your answer here should be CHCl3, chloroform. Okay, so chalo, chloroform is gone. Next, nucleic acids are the long chain polymer of, definitely this thing also you know, it is a nucleotide. So nucleotide is the monomer and nucleic acid is the polymer of it. Okay, now let's proceed with the next one, Van 't Hoff factor for KCl solution. So let's see how many ions it actually forms whenever KCl will be dissociated. So KCl, once it gets dissociated, KCl undergoes complete dissociation, you know this thing. So it will form K plus plus Cl minus. So altogether I am getting 2 ions, right? So Van 't Hoff factor is the same. So Van 't Hoff factor for this thing is going to be 2. So this option is gone. Next, the number of hydroxyl group present in glycerol. So let's see what is the structure of glycerol. So this molecule is glycerol, and you can see how many hydroxyl group, 3 hydroxyl groups are there. So definitely your answer is going to be 3. So this is also gone. Next, transition metals are known to make interstitial compounds. Formation of interstitial compounds makes the transition metal more. Here the option is going to be hard. Okay, so what basically happens here, whenever any kind of transition metal crystal lattice is formed, in that particular case some nitrogen, hydrogen, some other gases, they get trapped in between. Okay, so as a result of this, the metal gets a little brittle and hard as well. Okay, so the correct answer for this particular case is going to be hard. So this is all about the first part, section A. So before starting with the section B, just let me have a small water break. Let me bring my bottle, just a minute. So let's start with the section B, that is of 2-marker question. So let's proceed with the first question. So as you can see, what is Lucas reagent? And which class of alcohol does produces turbidity immediately with it? So you can say it's a direct question. So Lucas reagent, if you know this, then it's very good. If you don't know this, then definitely it's one of the board alert question. Please be careful about it. Most of the cases while analyzing the previous year question, I have found this question as a very common one. So in this particular case, let me just tell you the answer. This is ZnCl2 dissolved in HCl. Okay, please be careful, you are writing the entire thing. Means it's not only ZnCl2 that you are writing, you have to write ZnCl2 that is dissolved in HCl. Now let's move forward towards the next part. Which class of alcohol does produces turbidity immediately with it? So Lucas reagent, why it is used, just a small recap. This Lucas reagent is used to understand which degree alcohol is this. Is it primary, secondary or tertiary? And let me tell you one thing, this Lucas reagent works in SN1 mechanism with the alcohol. How? Let's say I am having 1 degree alcohol, RCH2OH, right? So if you add Lucas reagent here, I'm just simply writing ILR. So in this case, what will happen? Cl minus is your nucleophile here, right? So Cl minus will attack over here, and this OH is your leaving group. So leaving group will leave the system, and you will get RCH2Cl. So this particular thing gives you the turbidity. Now, if you can recall a little bit, SN1 reaction proceeds through carbocation intermediate, right? SN1 reaction proceeds through carbocation intermediate. So, more stable the carbocation, more amount of product, or you can say faster you will get the product, right? So in which case the carbocation is more stable, if you can recall, it's definitely 3 degree. So if I just make it like that, for this particular case, if Cl minus wants to attack, then once it will attack here and it will leave, initially as you know, SN1 reaction leaving groups leaves earlier, then the nucleophile attacks. So carbocation that will be generated, it is something like this. This is the carbocation that we will get out of it. But for this case, the carbocation is something like this, right? And 2 degree also you can know. So the order of the stability of carbocation is definitely 3 degree greater than 2 degree greater than 1 degree. So this carbocation is very much stable, and hence the product I will get out of it is faster, right? Hence the product I will get faster because it is coming through a very stable intermediate, right? So let's proceed towards the product. You can see here comes the overall question, overall answer in a single slide. So first one is Lucas reagent and anhydrous ZnCl2 and HCl. This is the reagent that you have to mention. So for the first case, whenever I am using 1 degree alcohol, because the carbocation is the most unstable one here, 1 degree carbocation is formed. So turbidity forms in 30 minutes. It takes time. For 2 degree, it takes 5 minutes. But whenever it's 3 degree, it's very stable carbocation, and hence immediate turbidity means immediate response to that reagent, immediate product you will get out of it. So your answer is going to be 3 degree alcohol. That's going to give you the immediate turbidity out of it. I guess you understood this. Let's proceed for the next question. So here write the SN2 mechanism for the conversion of chloromethane to methanol. Here also another thing I am just telling you, as my research on the previous year papers, this is one of the board alert question. Either SN1 or SN2 full mechanism you have to write, you have to keep practicing. Anyone you can expect in your exam. Okay, so let me give you a little brief how actually it works. Okay, so let's draw chloromethane. See, I am trying to show a little bit of stereochemistry. If you are not really very much familiar with it, then you can ignore as of now. I am trying to represent this thing in a 3D orientation. Okay, so this is how the chloromethane looks like. This is our chloromethane looks like. So now whatever I am having, let's say any kind of random nucleophile I am taking, just I am taking it as NU. NU is a nucleophile over here. Okay, so what will happen, it is an SN2 mechanism. It happens in a single concerted mechanism, single concerted step, right? And here one intermediate is formed in the transition state, right? In the same stage, nucleophile also attacks and the leaving group leaves the system, right? As a result of this, you will get a transition state out of it, and the beauty of the transition state is it is penta coordinated. Carbon is having usual valency 4, But here, for this particular case, SN2 reaction, carbon becomes penta-coordinated. Means it is neither it left the leaving group nor it accepted the nucleophile completely. It's a stage in between, neither the reactant nor the product. So it will look something like this. So definitely you can understand this particular stage is going to be very, very unstable for the carbon, because carbon likes 4 valency and here it is having 5. So this is the penta-coordinated transition state. So after that what happens? After that the leaving group leaves the system and nucleophile sits permanently, and as a result of this there comes an inversion of the configuration. So see, initially both the hydrogen this and this hydrogen, you can see it is facing this end, right? But whenever, just imagine, I am standing here, if someone just push me from the back all of a sudden, so I'll be a little bit ahead, right? So the same thing happens for the carbon as well. Nucleophile, it's something, it is pushing it a little bit all of a sudden, right? So from the front itself the chlorine will be left out and the nucleophile will take place from the back side. So here one important thing I wanted to tell, backside attack must be prominent in case of SN2 reaction. Okay, so let's write the product for it. So the product is going to be something like this is going to be the product of it, right? So as you can see, they are asking for methanol. In case of nucleophile you can use OH minus. Okay, you can use OH minus. So as a result of this you will get the product something like this. This is your methanol. So let me just show you in a graphical way how actually it looks like. See how nucleophile approaches and how it kicks out the leaving group from the system. Now just look at that. Here comes the entire description about the SN2 reaction. So my request for you people, pause your screen and whenever you feel like you should make a note of it, please make a note. So as I told you, nucleophilic attack is the primary stage, then it forms a penta-coordinated transition state and then the leaving group leaves the system, and this is how the reaction, this is how the overall reaction looks like. So definitely whenever a stable system, that is your methyl bromide or methyl chloride, chloromethane, whatever you want to take, that particular system, whenever it is very much stable initially, right? Definitely whenever carbon is having 4 hand, it is very stable. It definitely don't want, personally it doesn't want to go for a very unstable state. Like nowadays it's a winter, right? So it's not easy for you to wake up from the bed and just leave your blanket so fast, right? So for the carbon it is also the same thing. So carbon needs some time. So definitely from like a very stable state to go to an unstable state, it takes some time. So that's the reason the transition state formation is slow process, and then once the transition state is there, then from there again coming back to product is again fast. So this is how the reaction takes place. I guess you understood. Let's proceed for the next one. So here comes for the reaction H2 plus I2 gives 2HI. We have to draw a diagram showing a plot of potential energy versus reaction coordinate to explain the role of activated complex in a reaction. Okay, it's a very nice question, conceptual question. So let me show you how actually you should proceed and a little bit concept related to it. So this is your potential energy, okay, and this particular x-axis, let it be your reaction coordinate. Okay, so for this case, let me just start with the reactant. In general, if you just look at the system, any kind of system, in general, reactant or product, which one should be more stable? Just think about it. And if you thought like it is a reactant, then definitely you are going to be wrong. In general, the product should be more stable. If product is not stable, then why the reactant will proceed towards product? Right? So reactant is a little bit unstable than that of the product in general. Yeah, definitely reverse case also we see. In that case, we have to give some energy, right? But in general, reactants are not more stable than that of the product. So energetically, it is a little higher than that of the product. So if here it is the position of H2 plus I2, here lies the product HI, right? So let's say the enthalpy value here, let it be H1 and here let it be H2. Right, the enthalpy value here is H1, enthalpy of the reactant is H1 and here enthalpy of the product is H2. Fine. Now, how the reaction will take place? Definitely you are thinking it can go like this. But let me tell you, it will not come like this. It could come like this, no, it would be easier, right? So, but reaction actually doesn't follow this way. Why it doesn't follow this way? Let me explain a little bit. Basically what happens, it comes from reactant to product, through crossing this hill station, okay? Why? Because behind this a little bit binary collision theory, actually it's hidden, the concept is hidden in that, but we can explain it in a shorter way. Whenever two reactants, they are coming close to each other, they must have some effective collision. They must collide and the collision must be effective one. And not only the collision should be the proper one, the orientation must be the proper one, along with it some amount of energy. The minimum amount of energy the reactant or the colliding particle needs to proceed for the reaction, this is called the activation energy. So that energy if you are having, then only you will be able to proceed for the product. So let me just tell it in a very creative way. Let's say two of your friend, okay, they are meeting, they have some nice bonding, they have their vibes matched, the way I told the orientation must be matched, they have their vibes matched, but what no, they must go for some trip, some trek, right? But the problem is their family is not allowing or they are not having the money. Right? So if they are not having the money, they will not be allowed to go out, right? And this particular bonding will not work further, right? So this money or that allowance from the family, it's a huge matter. Okay, if it is nothing, if it is not there, then any kind of plan, any kind of vibes match will not work, right? So this activation energy is sort of the money in this reaction that is needed to proceed for the product. Okay, so from the reactant to product, this energy barrier is called activation energy. And here at the top of the peak, you know who is sitting? that transition state, most unstable state, right, where it is not the reactant, even it is not the product. Okay, it's intermediate, the transition state, the most unstable one, and thus energetically higher. I guess you understood. So this is the entire graph or the diagram, whatever you wanna say, it looks like. Okay, now let me give you an idea. See, if you want to find out the enthalpy of the reaction, the enthalpy change of a reaction, so definitely it's going to be that final minus initial that usually we do. So we are going to do it something like H2 minus H1, right? H2 minus H1. Now you tell me which one is greater. In this particular case, definitely H1 is greater, because you can see the energetically higher, right? It is energetically higher, it is energetically lower, right? So H1 is greater than H2. So definitely this enthalpy of the reaction value, because negative quantity becomes greater than that of the positive one, and hence the entire thing becomes negative. So enthalpy of the reaction value comes negative, it indicates it's an exothermic reaction. So I guess you understood the concept. Let's proceed. So this is the answer. You can just pause your screen and just make a note of it. And here in the transition state that I told you, that is basically the activated complex, that is actually termed as the activated complex. Okay. So let's proceed further. Okay, next question you can see, name the hormone released rapidly due to the rise in blood glucose level to keep the blood glucose level within the narrow limit. It's a direct question actually, you people must have heard about this hormone, it is nothing but the insulin. Let's proceed for the next one. Mention the number of amino acid present in this hormone. So let me tell you, overall number, if you just consider a mature insulin, if you consider a mature insulin, it is having total 51 amino acid in it. It is having total 51 amino acids in it. Now, to be more precise, insulin has 2 chain. So it is having, basically it is made up of 2 chain, okay, chain A and chain B. They are basically connected by disulfide linkage, right? In chain A, we are having 21 amino acid, and in chain B, rest 30. Okay, so just a little bit depth for this answer. Overall it's 51 amino acid. If you stop your answer there, you will get the full marks. If you know, just for your information, there comes 2 chain, they are linked with the disulfide linkage, and in chain A we are having 21 amino acid, in chain B we are having the rest 30. I guess you understood this. Let's proceed further. Okay, what are transition elements, and give an example of it. So this is also a direct question, simple theoretical question. So here as of now, whatever you faced in this particular case, 2 marker question, it's combination of physical, organic, inorganic and biomolecules as well. In 2 marker you can expect all of them. Okay, so see, if you are not well prepared in biomolecules, so you can leave the question because you have choice, right? So let's proceed further. What are the transition elements, and give an example. So transition metals we actually call the D block elements, okay, but not all the D block elements. Then what are they? The D particular D block must be partially filled by electron. Okay, why partially filled? Because the name itself is transition metal. Who is going to be who is in transition? Electron. If electron is not having enough room to do the transition, then why I will call it transition metal, right? Let's take one example of zinc. Zinc is having 3D10 configuration. All of you know this, right? So in this case, zinc will not be called as transition metal. Still it is there in the D block, right? Because where the electron will get space for the transition. There is no space left for the electron to move here and there, right? Then why transition metal? But if you just look into this example, if you look into the example of iron, we are having 3d6 configuration, right? 3d6 means it is having, the electrons are having ample amount of scope to move, and hence it's called as transition element. So as you can see, again I'm just going through the definition for you. Transition elements are those elements which have partly or incompletely filled n-1 d orbital in their elementary state or any one of their stable oxidation state. I guess the concept is clear to you. Let's proceed. So here we are finished with the part B. Make sure that you are catching up with the maximum marks up to part B, because whenever you are coming to part C, it's going to be 3-marker question, maybe some part marking you are getting, maybe a small part of this you don't know. There are some chances that the marks will be cut, but up to B, please ensure that you are getting the full marks. Let's start part C. So here comes the first question. Using valence bond theory, explain the geometry, hybridization and magnetic property of cobalt hexafluoride 3- ion, and the atomic mass of cobalt is given. So for these particular question, I will show you the thorough answer. Each steps I will do in front of you so that you can understand how actually you should proceed further to get the full marks in your exam for this type of question, right? So definitely, as you can see, it has 3 parts. See, geometry, hybridization and magnetic property. One you will predict and you will get 1 mark for it. Okay, so you can ensure all the 3 are correct and you are getting the full marks, right? So let's proceed for the answer. So initially cobalt is 27. So all of you know what is the electronic configuration. It is basically, I'm just writing the valence shell configuration for this. So it is basically nothing but 3d7 4s2, right? Now if you just look at this particular case, here I am having cobalt as +3 oxidation state. How I am getting it? Let's see. Let's say I don't know what is the oxidation state of cobalt. Let's take it as X. Fluorine is having -1, right? How many fluorine? 6 fluorine. So 6 fluorine of -1 equals to what is the overall charge? That is -3. From here, if you calculate X, it will come as 6 - 3, and hence X equals to 3. So from there I got to know that cobalt is +3 oxidation state. It is one of the major part that you know the oxidation state, and you must know how actually you should calculate it. Okay, so let's proceed further. So I'm having cobalt 3+, right? So 1 electron will be removed from 2 electron will be removed from 4s2 and 1 from here. So overall I will be having 3d6. So actually how it looks like 3d6, if you draw, this is my 3d. Let's write 4s, that is empty. let's write 4p as well. I will tell you why I am drawing all these things. And then let's say 4d as well. This is my 3d, this is my 4s, this is my 4p, and this is my 4d. Okay, so here I am having 3d6. So 1, 2, 3, 4, 5, 6. Right? 4 is 0, 4p 0, 4d 0. Right? Now what happens? Now so many things I have to tell here in this regard. Just look at the ligand. What is the ligand? Here the ligand is fluorine. My complex is COF6 3 minus. Here my ligand is fluorine, that is a weak filled ligand. It is an weak filled ligand. It's not that much strong. Okay, so we know from VBT, whenever I am having a strong filled ligand, it forces this electron to be paired up. Right? But whenever the field of the ligand is very weak, it will not force these electrons, these d electrons to be paired up further. Okay, so there will be no force pair. There will be no force pairing since it is an weak filled ligand. Right? So as a result of this, it will be as it is. Further hybridization will take place with these cells. Right? So here, how many ligand you can see? How many ligand I have to accommodate? 6. 6 ligands I have to accommodate. So let's count. 1, 2, 3, 4, 5, 6. So let's assemble them. Right? So what I am taking? I am taking 1s, 3p and 2d. Hence my hybridization is sp3d2. So hybridization is going to be sp3d2. I guess you understood this. Another one information just I want to share. As you can see here, the d orbital that is taking part in the hybridization, it is the nth d orbital, outer d orbital, not the inner one, not the 3d. 3d is the inner one, 4d is the outer one. It's a vacant one, right? 4d is the outer one. Okay, as outer d orbital taking place in the hybridization, hence we can call it outer orbital complex. Just an information. Okay, let's proceed for the next. So hybridization is sp3d2. I guess there is no problem with it. So whenever it's just a suggestion to me, whenever you will see you are having 6, coordination number 6, there is a chance that it will be octahedral most of the cases. So whenever you will be having sp3d2 geometry, I mean hybridization, then please without thinking twice just mark it as octahedral. Right? I just wrote it in short, OH means octahedral. Fine. So I got the hybridization, I got the geometry. Now we have to proceed with the magnetic property. So magnetic property, you know, who is the major thing that actually decides the magnetic property? These are the unpaired electron. Unpaired electron. So how many unpaired electron you are having, you have to check. So I am having 1, 2, 3, 4. So number of unpaired electron, I am having how many? 4, right? I am having 4. Right? So whenever you are having unpaired electron in your system, whatever the number may be, you are having unpaired electron, they are not paired up at all. So you can call them directly paramagnetic. They are paramagnetic in nature. Just for some extra information, if you are having all the electrons as paired up, you can call them diamagnetic. So once you are having paramagnetic compound, means you are having unpaired electron, then you can calculate the magnetic moment. You can calculate the magnetic moment of it. So what is the formula? Under root n into n plus 2, where n is the number of unpaired electron. Okay, where n is the number of unpaired electron. So from here, n is 4 into 4 plus 2. So from here you are getting 4 into 6, that is 24. So it will be almost 4.9 Bohr magneton. Bohr magneton is the unit of the magnetic moment. So here comes the full information and concept and how you should write the answer as well. If you write the entire thing, if you keep mentioning this is the hybridization, this is geometry, this is magnetic nature, and I am calculating the magnetic moment as well, your examiner will be more than happy. That's what you are targeting for, right? Pause your screen and make a proper note of it. I guess you are done. Let's proceed for the next question. Okay, again one big question. So I've seen people, it's been 6 years of experience I'm having with you people to deal with these people of your age. Whenever these children, they see this type of big questions, they avoid it. They are too lazy even to go through it, right? You also know this, it's true for you as well. So whenever you will see, okay, this much big question, let's leave it, we have options. But sometimes whenever the questions are big, maybe we have chances to get some part mark out of it. Maybe it is splitted in 1 plus 1 plus 1 like that. Okay, so don't be lazy. Please go through the entire question and try to answer it. Sometimes it will help you. Let's see. So heteroleptic complexes with coordination number 6 show geometrical isomerism. Okay, one by one, let's clarify the terms. Heteroleptic complex, what does it mean? If in the coordination entity, if in the coordination sphere, you are having different type of ligand with the same metal. See, here I am having two type of ligand, A and B. Right? If you are having different type of ligand, then this particular complex is called as heteroleptic concept. Okay? Let's proceed to the next term. Coordination number. What is coordination number? Coordination number means the number of ligand that is placed with the metal here. Okay? Number 6, so geometrical isomerism. What is geometrical isomerism? Geometrical isomerism arises because of the spatial arrangement of the molecule in 3D, right? And there should not be any kind of rotation, means restricted rotation, right? The circumstances must be restricted rotation, and in order to that we will see some spatial arrangement of the molecule. That is geometrical isomerism. Okay, definitely the formula is same, the arrangement is different, right? Okay, a complex Ma3B3 shows geometrical isomerism. Okay, if central metal ion M has +3 oxidation state, then you have to predict the denticity and draw the structure of two geometrical isomers of the complexes, and you have to name them. Fine. So first, one by one, let's solve it. I guess you understood what is heteroleptic complexes and coordination number 6. And if you understood coordination number 6, if you understood what does it mean by the term coordination number 6, means 6 ligands are there, then the denticity you can predict directly. Definitely they must be monodentate because you are having 6 ligands. There are no other option. So denticity denticity that I got, all of them are monodented. I guess you know what is monodented. Monodented means they have only one donating site, right? Let's proceed for the structure of the geometrical isomers. So while doing the geometrical isomers for this type of compound, for Ma3B3, this type of molecule shows two type of geometrical isomer. One is facial, another one is meridional. Let me at first draw you how actually the facial looks like and how actually the meridional looks like. In case you are not getting the proper overview how actually it looks in the 3D, then I will show you the 3D representation of it as well. Let's see. So facial, actually it looks like always remember facial will form a triangle at the same face of the octahedral. How? Let me just show you. If I connect this and this, here comes one triangle of this octahedron, and if I just connect them, here comes another octahedron. So you can see these octahedrons, these particular triangles are at the face of the octahedron. So this is facial. Okay, I will show you the 3D geometry as well. In 3D how actually it looks like, it will be even clear to you. Now let me just draw the another one, that is the meridional one. This is the meridional one. So here actually what happens, here the two triangle, they are in accordance to the arc of the octahedral or at the meridional position of the octahedral. Okay, so if you just make the triangle out of it, so here comes one triangle, right? And you can see there comes another triangle at the back side of it, right? It feels like they're cutting each other, right? Now let me show you. This is how they looks like. This one is your meridional and this one is your facial. I guess the concept is clear and you can visualize the isomer as well. So once the visualization is clear, you can nicely draw the structure in your copy. Let's proceed further. Here comes another very common question. Okay, I guess I told 5 times very, maybe. Anyway, if you counted, then please let me know in the comment. And this is another board alert question, I can tell. Direct question, theoretical question. Okay, there are full chance that you are securing full marks in it. Okay, so what is lanthanide contraction? Mention to consequence of it. Definitely direct answer I will show you, but before that let me just explain a little bit so that you can connect this with the concept as well. So what happens basically in the lanthanides, we are having D and F orbitals, right? So D and F orbitals are very poor shielder, right? They are very poor shielder. They can't shield the nucleus, right? So nucleus becomes very much open towards the outermost electron. See, actually what happens if I am here, let's say I am the teacher in the class, okay, and I want to have a look at the last member sitting in the last bench, and in the middle there are so many students, so many benches, and there are so many students, they are sitting together, right? So it will be difficult for me to have a look at the last people sitting in the last bench, right? Agreed? But if in the intermediate benches the students are not well assembled, they are here, there, someone is sitting there, okay, they are not well assembled, they are scattered, right? They are diffused, delocalized, then I can directly see the last student sitting there, right? So the same scenario is applicable in the atom for the lanthanide contraction as well. So what basically happened in the center, like in the position of mine as a teacher, just imagine nucleus sitting there, and nucleus want to attract the last electron, the outermost electron. So if in the middle there are electrons to shield it, then the nuclear force will not be that much. But here the number of electrons are there are number of electrons, good numbers of electrons, D and F, so many electrons, but they are scattered, they are diffused, because in order to avoid the internuclear repulsion, they are diffused, delocalized. So nucleus is open to the outermost electron, right? So with the full force that we call as effective nuclear charge, this particular nucleus, let's say in the middle we are having so many electron as a cloud, you imagine, then it will be clear for you. Then it will be pulling the last electron with the maximum effective nuclear charge, right? As a result of this, what will happen? So if the outermost electron gets contracted, gets attracted more by the nucleus, the overall radius of this particular atom will be smaller, because it is getting pulled inside. This is the lanthanide contraction, okay? Because of the presence of D and F electrons, they are being diffused, delocalized. The nucleus is having very high effective nuclear charge on the outermost electron, right? As a result of this, the radius of the atom decreases, okay? Let me show you where actually it affects most. Here I am just keeping one reference for this case. Just look at this. We know atomic radius keep increasing top to bottom, right? Top to bottom, the atomic radius increases, the size increases. So if you just look at this particular case, from zirconium to hafnium, the size should increase as well, right? Means from here to here, from zirconium to hafnium, from niobium to tantalum, molybdenum to tungsten, the size also should increase, right? But it doesn't happen like that, right? It doesn't happen the way it should increase. Rather, it becomes quite similar. It doesn't increase, right? This particular thing is called lanthanide contraction, okay? And this is one of the outcome of the lanthanide contraction, that also you saw there was a part question with it. What are the consequences of it? So here you can see, just after the lanthanides finished, we are having hafnium here. So hafnium is the first element that is facing the effect in a maximum way, right? As a result of this, you know what happens? The zirconium and hafnium, they become chemical twin. When we call someone twin? When they are similar in nature, right? When their properties, how they look like, everything becomes similar. So what happens, you know, the zirconium and hafnium, the size, the chemical property, everything becomes so similar because of this contraction, that we call them chemical twins. Sometimes from the ore, we can't even separate them. We can't even separate zirconium and hafnium as two separate elements. This is one of the consequences. And another one consequences, you can see the basic character of the basic character of the hydroxide, right, that decreases, because with the contraction itself the ionic radius it decreases. So in accordance to Fazan's rule, the basicity of this particular case decreases. So for the Fazan's rule, keep watching. We will make a different video where there will be the topics related to Fazan's rule and all. Definitely these things are related to class 11th portion. For the KCET purpose and for the Comet K, please keep looking on this channel. We will make separate video on the application of it. So as of now, just remember, as the ionic radii decreases, as a result of this the covalent character decreases, and hence basicity or basic character decreases as well. So let's look into the answer. You can see. Okay, so I'm having the next question. How many square pyramidal units present in decacarbonyl dimanganese 0? Write its molecular and structural formula. Okay, so very nice question, moderate to difficult level question. If you know this, then only you can proceed with the things. So at first let me tell you, while dealing with this type of question, you must have the idea about how to nomenclate the inorganic complexes. Okay, so definitely whenever you are having dimanganese means 2 metal you are having, 2 metal along with decacarbonyl means 10 carbonyl, and 0 indicates the oxidation state of the metal, means manganese must be 0 here, right? So I guess you guess the molecular formula. So one by one we will see the question. You can see molecular formula is Mn2CO10. I told you, I explained the nomenclature and I told you this is going to be the formula. Now in order to find out the structural formula, it kind of looks like this. There comes a manganese bond, metal bond, okay, and this carbonyl, they are oriented in such a way it feels like two pyramidal part, they are uniting by this particular bond. Let me show you this particular structure in a better way. Just look at that. Here I am having 1 Mn, here I am having second Mn, right? So now they are connecting with a bond. Fine. So here I am having 1 carbonyl, here I am having 1 carbonyl, here carbonyl, here also carbonyl, here also carbonyl, right? Just look how the pyramid is formed. See, here comes one pyramid, right? And here also in the similar way I am having another pyramid. That is the back side CO. Okay, so here I am having on this, on this, on this. So just look at the pyramid structure here. This is another pyramid. They are connected in a single line. Okay, so definitely you must know the structure of it, otherwise it will be little difficult. So in accordance to the structure, you can see how you should represent 1 carbonyl towards, 1 carbonyl backward. Here also 2 carbonyl towards, 2 carbonyl backward, and 2 carbonyl, you can see here 1 carbonyl on the plane, here I am having 3 carbonyl on the plane to make it proper square pyramidal. I guess you understood. Just go through the description of this. I guess it will be clear to you. Let's proceed for the next question. Okay, so here also it's a board alert question. Okay, it's a direct question. The question comes that is related to the preparation of the potassium dichromate and KMnO4, the preparation of K2Cr2O7 and KMnO4, very, very important zone, and from here direct question comes. So if you know the reaction, then you can give it a try. Okay, so as I request you, please write the particular reaction several times in your copy and practice it. Okay, so that whenever you are writing it here, like this type of fill in the blanks type of question will come, you should not be messed up with the stoichiometry, right? So first, even without knowing this, I can just give one guess. You can see this side sodium is there, here also sodium is there, right? That side carbon, this side carbon, oxygen is there, oxygen is there. So definitely in the blank some compound is there where iron should be and chromium should be, right? Just a trick to remember. Okay, so here actually sits Fe Cr2 O4. Okay, and if you balance it, the stoichiometry comes 4. This is called chromite, the ore. Okay, and let's proceed for the next one. So this is nothing but the MnO2. It is fused with KOH, right, and it is also oxidized with air. So for this particular case, I will get K2MnO4, and the stoichiometry will come as 2 plus H2. Let me write down this entire reaction properly, then you will get the clarity why 2. So basically MnO2 plus KOH plus I am having oxygen, right, because you can see it is fused with KOH and oxidized with air, that's why, and you are getting K2MnO4 plus H2O, right? So now if you just balance it, here I will get 2, here I will get 4 KOH, and as a result of this you have to maintain 4 potassium this side as well. So 2 K2MnO4, and I guess water is already balanced. Yeah, 2 H2O, 2 H2O, it should be there. Okay, so let's proceed for the next one. This is nothing but the thermal decomposition reaction of KMnO4. So if you just decompose it in this temperature, you will be having K2MnO4 plus oxygen, here plus MnO2. Okay, I guess you understood this. It's a direct question. So let's proceed. So next question it comes, mention 3 factors that affect the rate of a chemical reaction. So there are several factors several factors, you can just take any 3 of them and you can proceed. Let's say I have taken here the concentration, the temperature and the surface area. So as you know, if you increase the concentration, if you increase, it is appear to be like if I am having more number of reactant, I will get more number of product, right? So the rate will be increased. But let me tell you, it's an experimental concept from where the order actually comes. Means all the reactant concentration will matter or not. It's an experimental quantity. In general, you can tell that okay, chalo, if you increase the concentration, then definitely the rate should increase. Okay, another factor, it is one of the most important factor, that is the temperature. So temperature, if you increase, if you just studied the Maxwell-Boltzmann distribution curve, from there also it is clear, and from the Arrhenius equation also it is clear that rate depends upon the temperature. So if you increase the temperature, the kinetic energy of the molecule, the colliding molecule will increase, so there will be more number of collision. So as more number of collision, hence the reaction rate will be faster. Next is surface area. Surface area means if the reactants, if they can come in contact properly, then only the rate increases. So sometimes what we do, we sometimes make it a dust, we grind the particular reactant molecule so that the surface area increases. You can see for solid reactant, increasing surface area increases the reaction rate. So that's why grinding a solid, that's why whenever you are having a solid reactant, grinding a solid into powder, for example, exposes more particles to the other reactant, leading more frequent collision. I guess the things are clear. Direct question, any three you can take, otherwise catalyst and all these things are there, you can just write any three of them. Let's proceed. Okay. Name the concentration term which is commonly used in the medicine and the pharmacy. Write the definition and the mathematical equation for the concentration term. So if you just see a tube of ointment, okay, so the most common term that you see, weight by volume percentage, okay, that is the concentration term they use most. So here you can see the definition, you can see mass by volume percentage is a way of expressing the concentration, means how much gram of solute is dissolved in 100 ml of solution. Okay, 100 ml of solution, total volume must be 100 ml. Okay, and this is the particular mathematical equation. So for this case, please be assured that in the numerator you must have the unit gram, and in the denominator part it is used as volume, hence the unit should be ml into 100. I guess it's clear to you. Let's proceed for the next one. Here comes a very easy question that you are studying from 10th grade. You can see, depending on the magnitude of conductivity of the materials, mention the three types of material with an example. You can see type of material, conductivity, and example. We are having conductors, semiconductors and insulator. These three types. For conductors, conductivity is very high, definitely. There are free electrons on the surface of the particular metal, they actually conduct the electricity. So very high, and here you can see copper, silver. With this we actually prepare the wire, right? So now you can see semiconductor. Semiconductor is the conductivity is in between the conductors and insulator. So it is basically silicon, germanium, and here you can see insulator, the conductivity is almost 0. So rubber, glass, wood, they are called as insulator. It's a direct question, very easy question. Let's proceed for the next one. Okay, so here comes the next question. You can see the diagram shows that when iron is exposed to atmospheric air. So we have three parts of this question. First, name the phenomenon involved in this diagram. So I guess you already guessed it. So whenever iron is exposed in the air and also the water vapors are there, you can see. So definitely it's nothing but the rusting. Okay, so write the atmospheric oxidation reaction of iron and mention any one of the method to avoid this phenomenon. So just look at the formula I already have written here. So basically iron reacts with oxygen and some amount of H2O to give you Fe2O3 dot XH2, that is a crystalline water present in the rust. Okay, this is the brown color rust formula that actually we get. Okay, now you can see how to avoid this rusting. So if we actually hide the iron surface, cover it. Okay, how you should cover it? Either you can do painting. So just a coat of painting can avoid it will be a barrier to the surface area of iron to the atmosphere. Okay, and hence you can prevent rusting. Another process is galvanization, means another one metal coating should be there on iron. Usually we do zinc coating, right? Another is oiling or greasing. So we can apply a protective film of grease or oil to avoid these particular things. So you can just pause your screen and make a note if you wish. Let's proceed further. Okay, fine. So here we are going to start the section D. Just let me have some water, then we will start with the section D. So let's begin with section D. So this is the 3-marker question. So the first question is, write the Howard structure of maltose and why they show reducing property. So for this particular case, you can see it is a disaccharide of 2 particular glucose. Both of them are alpha D glucose. Okay, this is also one alpha D glucose and this is also alpha D glucose. So what basically happens here, in carbon 1, this carbon 1 made a glycosidic linkage with the carbon 4 of the second alpha D glucose unit. So from here you can see one OH and one hydrogen gets released in the form of water. As a result of this, here you will see 1,4,1,4 glycosidic linkage. So this is the structure of maltose. So overall Haworth projection that you can see, it is actually written like that. So the front, the bond is towards yourself, that's why it is denoted with the solid bond. Okay, so now here you can see next part of this question is, why they show reducing property. So let me tell you, we have 2 alpha D glucose linkage, right? So for this, one alpha D glucose, we have carbon 1, and that carbon 1 is making the glycosidic linkage, right? But another alpha D glucose, whenever you are looking at, this is one anomeric carbon, that carbon is free, right? So this free carbon opens up the ring and gives one aldehydic unit, right? That particular aldehydic unit further gives one electron, and that electron will work as a reducing agent. So that is a property of a reducing agent. No, it will donate some electron. So let's see in the next slide. Here, this particular alpha anomer, you can see it is open, right? So this, when the ring opens up, one free aldehydic group you will end up with, and that free aldehydic group has a capacity to reduce the Tollens reagent, Fehling's reagent. Okay, so just go through these things once, pause your screen if you want to note it down, and please make a note of it. I guess you are done. Let's proceed for the next one. Here comes the next question. You can see, what are the fibrous protein? Name the protein present in the hair. So first of all, what is fibrous protein? It is a protein that is long, that is insoluble, and it provides a supportive framework, right? So here you can see the definition is given properly, and this type of protein usually we can see present in our nails, hairs, claws, horns, etc. So and another protein that it's mentioned in the second part, name the protein present in the hair, that is basically the keratin. Okay, it's one of the fibrous protein, and you can see this is some structure of the keratin, some structure of the fibrous protein that I have added so that you can get some idea how actually it looks like. It's something like a framework that supports something. Okay, so let's proceed for the next one. So here comes write the 3 steps involved in acid catalyzed dehydration of ethanol to ethoxyethane at 413 °C. So let me tell you, for these type of mechanistic answer type of question, depends upon the steps. Focus on each and every steps. So at first let me start with the step 1. So first step for this particular case is protonation. So definitely we have to start with the ethanol, that is my CH3 CH2 OH, and I'm using acid as a catalyst, right? I'm using acid as a catalyst. So let me add H plus. So definitely the lone pair of oxygen will takes up this H plus and it will form CH3 CH2 and OH2 plus, right? So using H plus as a catalyst is just to make OH a very good leaving group. Okay, in the next step we will do nucleophilic addition. This is my step 2. Here we will do nucleophilic addition. So here basically what happens? Here another ethanol molecule will attack on this particular thing. So here I am having ethanol and I had that one, that protonated version of ethanol. So this lone pair will attack on this carbon and this will leave the system. As a result of this, I will get something like this. CH3, CH2. Here I already had OH in my system. Along with that, this unit will be added up. CH2, CH3. And as you can see, oxygen is making 3 bonds. So let's put some plus charge over here. Okay, step 3 and the final step. This is basically deprotonation. So for this particular case, you are having the protonated version of the ether. So what it will do, this particular hydrogen will be leaving the system, giving its bonded electron to the oxygen. So the H plus will be regenerated in the system. That will further take part in the initial stage. So here you can see I'm ending up with the ether. CH3, CH2, O, CH2, CH3, right? So this is nothing but my ethoxyethane. So I guess you understood this mechanism. Let's proceed for the full answer. Here comes your full answer. How you can end up with the ethoxyethane, or you can say diethyl ether, starting from ethanol. Pause your screen, and if you wanna note something, please note it down. I guess you are done. Let's proceed further. Here comes the Cole's reaction with the equation. So it's a direct question, and let me tell you, it's a high board alert question. Okay, Cole's reaction is one of the most important thing that usually it comes in the board. Here comes the reaction. We start usually with phenol and then we make the sodium salt of it, right? So sodium phenoxide, then we charge it with CO2 and H plus, and we end up with the salicylic acid. So this is the overall equation for the Cole's reaction. Let's proceed further. Here comes the next one. So when alkyl chloride react with the sodium iodide in dry acetone gives alkyl iodide. So name of the reaction, write the general equation of the reaction and mention the role of dry acetone here. So as you can see, this is the reaction. Any kind of alkyl chloride, you can take RCl and treat it with the sodium iodide and give dry acetone as the reaction media, and that will end up with the iodide, alkyl iodide, right? And you will get the NaCl precipitation Fine. Here the name of this overall reaction is Finkelstein reaction. It's a name reaction. Sorry. It's a name reaction, that is Finkelstein reaction. Okay, or Finkelstein halide exchange reaction sometimes, because two halogens, they are getting exchanged in this reaction, right? So let's proceed further. Last part of the question was, what is the role of dry acetone in this case? Okay, so first of all, this dry acetone, this is a polar aprotic solvent. Polar aprotic. Aprotic means it will not donate any kind of proton. So in this particular solution, it will help the nucleophilic attack at first. You can see sodium iodide is soluble in dry acetone, right? And it will allow the I minus to act as a nucleophilic. So nucleophilic attack will be more feasible if I use this medium. Another thing, as you can see, the last NaCl or whatever your starting material, in accordance to that NaCl, NAB or whatever, it will be precipitated out from the media, right? It is not soluble in acetone, so it will be precipitated out. So once one product will be removed in the form of precipitation, then in accordance to Le Chatelier principle, the reactant will think, okay, I don't have enough product that side, so the reaction will be more forward to give you more and more product, and NaCl or NAB or whatever it will be precipitated, it will be removed from the media, right? And reaction will be proceeding more towards forward direction, right? So as a result of this, the reaction will proceed towards a completion. So this is another reason why we use acetone. And another thing, dry acetone, it stops, it prevents different type of side reaction like hydrolysis of the alkyl halide. This type of reaction, it prevents whenever there is dry acetone. So just look into it, make a note if you wish. Let's proceed further. Here comes the next one. It is also a direct question. You can see what is meant by racemic modification. So racemic modification or racemic mixture, racemate, all of them are the same word. Okay, and why they are optically inactive. What is the reason behind it? Okay, so first, what is the racemic mixture? Whenever you will see both the enantiomer is present in 50-50 or in equal amount, right? So we know that superimposable mirror image, right? Whenever I'm having one optically active compound, we are having superimposable mirror image, and those are called enantiomers, right? So for those particular case, if you are having D and L both in 50-50%, in that case you can tell that I am having a racemic mixture, right? So now why they are optically inactive? The reason of being optically inactive, one of the reason we call it external compensation. So what basically happens here, 50% D, if it rotates the plane of polarized light in a clockwise direction, then other 50% of L, it will rotate the plane of polarized light in the anti-clockwise direction. So two different type of rotation will compensate each other, will cancel out each other. As a result of this, the net optical activity will come as 0. Just look into the solution. I guess you will get the better clarification. I guess it's fine. Let's proceed for the next one. So here comes the next question. Which type of amines answers for carbylamine reaction, that is a isocyanide test. Explain this reaction with an example. So here just let me tell you, carbylamine reaction is only possible in case of primary amine, means whenever the nitrogen, that particular amine nitrogen, is attached with another 2 hydrogen. 2 hydrogen must be there to proceed with the reaction. So this is a very specific test for amines, and you can see secondary tertiary amines, they do not undergo this type of reaction because of the lack the necessary hydrogen atoms attached to the nitrogen. Fine. Now one example that I can give here, that is the aniline taking part in carbylamine. So aniline, when it is treated with chloroform and KOH and it is heated, we will end up with isocyanide, and that will give you a very strong foul smell. Okay, very foul smell. That is the identity that okay, this is a primary amine, and in my media I am having isocyanide compound right now. Okay, I guess you understood this. Let's proceed further. So here comes a reaction. You can see you have to identify the compound X and Y in the following reaction. So definitely whenever it is aniline and it is treated with NaNO2 plus HCl, okay, and this particular temperature you can see 0 to 5 degrees Celsius. So this is an identical condition to prepare benzene diazonium chloride. Okay, so whenever so definitely this particular X is going to be benzene diazonium chloride. And now you can see after treating with something I am getting iodobenzene, right? So definitely this particular thing is going to be Ki, right? So benzene diazonium chloride on treatment with potassium iodide will give you iodobenzene, and you can see KCl and N2 will be there as a byproduct. I guess you understood this. These are the clear-cut questions. I don't think that you should have that much of problem to face this type of question. So here it comes the name reaction. You can see you have to tell the name of the following reaction. So first one, you can see this particular reagent is the identity. It's the Rosenmund reaction. For the second case, anhydrous AlCl3. Just a minute. Anhydrous AlCl3 is the identity of the Friedel-Crafts reaction, and you can see I am having one acyl group to be substituted, right? So you can see this is a Friedel-Crafts acylation reaction. Here you are having zinc mercury amalgam in the medium HCl. This is the identity of the particular reaction. It is a Clemenson reduction. I guess the things are clear. Let's proceed for the next one. So here comes the question, among methanol and ethanol, which one undergoes Cannizzaro reaction? So if you just write the formula of methanol, it is something like this. That is a formaldehyde. And if you write the formula of ethanol, it is something like this. This is the acetaldehyde, right? So let me tell you, one of the most important criteria for a reaction to proceed with the Cannizzaro reaction is there should not be any kind of alpha hydrogen in my system. Okay, means non-enolizable aldehyde group I need. Okay, so here if you just look at this particular system, carbon is directly attached with any hydrogen, so no alpha hydrogen for this case. But here I am having 3 alpha hydrogen. Here I am having 3 alpha hydrogen. So for this system, Candijaro will not work. For this system, definitely Candijaro is going to give you the result. I guess it's clear to you. Let's proceed for the next one. So this type of problem sometimes student feels a little tricky, because here you have to identify like some sequential reactions and some reactant and product, some reagent, they are missing. By looking at the hints that is given in the question, you have to identify what is A, what is B, what is X, like that. So here if you just look at the compound, A has the molecular formula C7H8, that is heated with alkaline KMnO4, followed by acidification gives compound B of the molecular formula C7H6O2. This compound B turns blue litmus to red. The sodium salt of the compound B is heated with the reagent X and gives hydrocarbon C of molecular mass 78 gram. So definitely you have to find out that A, B, C. Okay, so let's solve it one by one, or sometimes we may go like a backward direction. We may go towards backward, right? See, first you can see B turns blue litmus paper to red. So definitely blue is a acidic molecule, right? And whenever you will see that it's the carbon, number of carbon is 6 or more than 6, please you can assume that there must be a benzene ring. So if I start with a benzoic acid, that's an organic acid, the molecular formula of this benzoic acid is also C7H6O2. Okay, so if I start with benzoic acid, because it is an acid, it can turn the red litmus to blue, right? Sorry, to blue to red. It can turn the blue litmus to red. So now this is my B. This is my B. Now from something B came. How it came? By heating it with alkaline KMnO4. Right? Alkaline KMnO4 is a very, very strong reducing agent, a strong oxidizing agent, right? So whatever the alkyl group may be, alkaline KMnO4 can oxidize it completely. So definitely I can start with this thing, that is none other than toluene, that will give you the benzoic acid after the treatment of alkaline KMnO4. And the molecular formula is quite same as well. Now let's look forward to C. They're saying that the sodium salt of the compound, okay, if this particular acid gives you the sodium salt, it will be sodium benzoate, right? From here I am coming back to something whose molecular mass is 78 gram, sorry, whose molecular mass is 78 gram. So 78 gram represent actually benzene. Okay, if you just calculate the molecular weight of benzene C6H6, this will come as 78 gram. So how I can come from sodium benzoate to benzene? So you have to treat this with soda lime. So what is soda lime? It is basically NaOH. It is a mixture of NaOH plus calcium oxide. Okay, so I guess you understood this. So this is my C. Let's proceed for the next one. Okay, we have another counterpart. Identify X and mention its role in the reaction. So as you can see, here X is none other than this soda lime, and it actually performs decarboxylation. It actually performing the decarboxylation reaction that will give you from the sodium benzoate to benzene. I guess you understood this. So let's proceed for the next one. So now we are proceeding towards section E, that is also 3 marker, and here we will face the numerical type of question. Let's proceed. Here you can see the first problem that we are going to deal with. So you can see we have a reaction that is 2Fe3 plus 2I minus will give you 2Fe2 plus I2. E0 cell value is given for this particular case. We have to find out the log Kc. So whenever the numerical type of problem will come, my suggestion to you people, sometimes just by looking at the problem without analyzing, you come to the conclusion that okay, I won't be able to do it. I don't know the formula, I don't know where to put the values, I don't know these things. But trust me, once you just note down the values whatever it is given, then 50% work will be done. So let's write down what actually are given. 0.236 temperature is also given. Okay, so now we have to link E0 to log K. So we know the formula. E0 cell is equals to 0.059 divided by n into log Kc. So simply just substitute the value over here. Let me just tell you in brief how this particular thing actually comes from del G0. So del G0 we can write minus NF E0 cell. And also del G0 in another form we can write minus RT ln Kc. Right? So from these two we can equate these two sides. So NF E0 cell is equals to RT ln K. Right? So from there I am getting something. E0 cell is equals to RT ln K divided by NF, right? So from here I can write E0 cell equals to, see, if I convert ln to log, I have to multiply these things with 2.303. So let's multiply 2.303. If you put the value of R as 8.314 and T value as 298 Kelvin and Faraday's constant as 96500 and N value here comes 2. So here it will be log Kc. Okay, so overall the reaction, if you just put all the value and you just calculate it, you will get 0.059. So from here only the equation came. 0.059 divided by n equals to into log Kc. So that actually we are going to use here. Fine. So now what is our role? Just to put the value. So E0 cell value is given here 0.236. So E0 cell into n, what is the value of n here? You can see if you try to convert Fe3 plus to Fe2 plus, Fe3 plus is getting converted to Fe2 plus. So here 1 electron. Okay, and here in the second case you are having I minus to give you I2, right? So here you have to add 2 electron. So here 1 electron, here 2 electrons. So first equation you have to multiply with 2. So overall the exchange of electron value, it is coming 2. So N value for this reaction is coming 2. So what is N? N is basically number of electron exchange. Fine. Divided by E0 cell, right? Divided by 0.059, okay, equals to log Kc, right? So now if you just simply calculate this entire thing, you will get the log Kc value is almost equals to 7.98. Okay, I guess you understood how to proceed with this. Let's proceed for the next one. Here you can see, again I am telling you the same thing, whatever the datas are given, please at first note them. So here they have given a first order reaction rate constant value at 600 Kelvin temperature and energy of activation value also given. Calculate the rate constant at 700 Kelvin. So what are the things given? Let's say K1. K1 means whenever the rate constant is given at 600 Kelvin. So K1 value is given how much? 2 into 10 power minus 5 second inverse. Okay, and temperature, that is T1, is given something 600 Kelvin. Fine. T2 is given 700 Kelvin, but K2 we have to find out. Okay, so you have to think which equation that we studied that actually is a link, is a connecting link in between rate constant and the temperature. So if you have guessed it, you guessed it correctly, I guess. It's a Arrhenius equation. So let's put it. Log K2 by K1 is equals to EA divided by 2.303 R into T1 into T2, here T2 minus T1. Now nothing is there, we just have to put the value. So if we just put the value, so it was log K2 by K1, right? Log K2 by K2 we have to calculate. What was the K1? K1 was 2 into 10 power minus 5. 2 into 10 power minus 5 equals to, if you proceed further, here I am having the activation energy value as well. So activation energy value they have given something 209.8 kilojoule per mole, right? But I will convert it to joule. So that will give me 209,800 joule per mole, right? Let's put the value there. So here I am going to put what was the value? 209800 joule per mole divided by, here I will be having 2.303 into R value is 8.314 into here T2 minus T1. So 700 minus 600 divided by 700 into 600, right? So if you simply calculate it, log K2 by 2 into 10 power minus 5 will give you, if you just calculate the entire thing, this will give you something 2.608. Okay, so now let's do antilog. K2 into 2 into 10 power minus 5, antilog means 10 power 2.608, right? See, now 10 power 2.608, these almost come close to 405.5. Okay, so now K2 value should be 2 into 10 power minus 5 into 405.5, and K2 if you calculate from there, it will be almost like 8.1 into 10 power minus 3 second inverse. Okay, so sometimes there comes a question like how I calculated this thing, right? So in PU board examination, the log tables will be given. From there also you can calculate, or else there comes some methods that we actually use. Here you are having 10 power 2.608, right? So if I want to calculate this, I can do it something like 10 power 2 plus 0.6. See, this entire thing you can't calculate. You have to approximate it up to 10 power 2.6. So these value you can calculate. Okay. So close by value you will get not that much difference actually. So from here, by putting the law of indices, we can write 10 squared into 10 power 0.6, right? 10 squared point, here we can write 10 square into 10 power 0.3 whole square, right? So now what we can do, this 10 power 0.3, few values like 10 power 0.3, 10 power 0.5, 10 power 0.7, this value you should remember. So 10 power 0.3 almost, it's almost 1.99 something, so we can approximate it as 2. So 10 square into 2 square, so it will become along with 400 approximately. So see, here the value is 405.5, so close by value you will get, okay, if you don't want to use the calculator. In case log table, so if you can use the log table, so you can get the value out of it. I guess you understood, there is no problem, I guess. Let's proceed further for the next one. Okay, so Henry's constant for the molality of methane in benzene at 298 Kelvin is given. Calculate the mole fraction of methane in benzene. Okay, it's very easy question actually. Direct Henry's law you have to apply. So what was Henry's law? Partial pressure is directly proportional to the mole fraction. So to remove the proportionality sign, we put some constant, and that is called Henry's constant. That is a Henry's law. So everything is given in the question, you can see. That is Henry's constant value is also given, and partial pressure also given, that is 760 mm of Hg, right? Divided by the kh value is also given, that is 4.27 into 10 power 5, that is equals to mole fraction, right? So from here, mole fraction value, if you calculate, it's a simple calculation. If you put it into your calculator, you will get the value. It will come as approximately it will come as 1.78 into 10 power minus 3. Okay, as you can see, both the units will be cancelled out, so mole fraction is unitless quantity. Okay, so this thing, please be careful while writing the units. Okay, that's going to be a major part to determine the marks. So you have done everything, but you didn't mention the unit. 1 mark will be cut. Okay, please be careful about it. Write the proper unit. Let's proceed further. Here comes another one. Calculate the limiting molar conductivity of Cl minus ion by using the data, that is limiting molar conductivity of Ca2 plus is given, and for CaCl2 is also given. So simply we are going to apply the cold rush law here. So basically if you just write the del m0 of CaCl2, it is basically the individual contribution of Ca2 plus Ca2 plus, and here 2Cl minus, because you know, if you just simply split this thing, it will be dissociated into Ca2 plus 2Cl minus, right? That's why this 2 stoichiometry came here. So this value is given here. You can see 2 271.6 Simon centimeter square mole inverse. And here also calcium 2 plus value is given 119.0 Simon centimeter square mole inverse plus 2 into lambda Cl minus. Okay, so lambda Cl minus is going to be something like 271.6 minus 119.0 divided by 2 Simon centimeter square mole inverse. So that is the thing. If you calculate it, lambda Cl minus, you will end up with something 76.3 Simon centimeter square mole inverse. That's going to be your answer. I guess you understood this. Easy question, direct application of Kohlrausch law. Let's proceed further. Here you can see, calculate the osmotic pressure in Pascal exerted by a solution prepared by dissolving 0.925 gram of polymer of molar mass this in 500 ml of water. Fine. Here directly apply the formula of osmotic pressure, right? This is pi equals to CRT, right? So C can be written as N by V, right? N is the number of moles and V is the volume. Okay, now again let me just break it down. Number of moles can be written as given weight by molecular weight, and rest of the thing you write as similar. Here V, here R into T. Now just nothing, put the value whatever is given there. Okay, be careful, T must be written in Kelvin. Okay, so if you just put the value over there, 0.925 gram. Okay, molecular weight is also a big one, that is 185,000. Volume we will consider in liter, so we can do 0.500 liter directly. I am doing it. This is also gram. And here let's put the value of R. R is given 8.314 into 10 cube Pascal liter K minus K inverse into, so 37 degrees Celsius means 310 Kelvin. So entirely if you calculate, your answer will come, see every unit will be cancelled out with each other. See, liter, Kelvin will be cancelled out, only you will end up with a Pascal, right? So Pascal is the unit of pressure, you people know. So here you will end up with 25.79 Pascal. Okay, I guess you understood this. Let's proceed for the next one. So here comes the next problem that we are going to proceed with. Here you can see, analyze the given graph drawn between the concentration of reactant in mole per liter versus time in minute. Calculate the average rate of reaction in terms of minute and seconds. Okay, so we actually don't need that much data. We will just work on the first one and the last one, means initial time and the final time. Okay, so if you just look into it, here this is the initial time. So let's say it is my T1. T1 is the initial time, that is 0. At that time, the reactant concentration, let it be R1, it is how much? You can say at 0 time it is 1.6. It is 1.6 mole per liter. Fine. And another one you can see, whenever it is T2 means let's say final time, this is 30 minute. Okay, so as you can see, the reaction coordinate is given in minute only. Fine. Now you can see final reactant concentration at 30 minute, it is 0.2 mole per liter. Right? Now I'm simply going to apply the formula of rate of the reaction. So here you can see the rate of the reaction. Definitely we are going to write it with respect to the reactant. So we know with time the reactant concentration keeps decreasing. So one negative sign we have to apply here, and here the change in the reactant concentration divided by change in time. So from here I can write it is nothing but the final minus initial, right? Final minus initial divided by T2 minus T1, final time minus initial time. Now we have to just put them all together. So R2 here it is 0.2 minus what is R1 here, 1.6, right? And T2 is 30 here minus T1 is 0. Now here you can see mole per liter, and here you can see denominator is in the unit of minute, so you can write minute inverse, right? So from here I am getting overall 1.4 divided by, because minus will be plus anyway, so 1.4 divided by 30, that is mole per liter per minute, right? So if you calculate this, it will come almost equals to 0.0467 mole per liter per minute. Fine, this is one of the answer. And another answer, let's proceed. I had, let's say, 1.4 divided by 30 mole per liter per minute, right? So here I have to convert it to second, because you can see in the question they are asking for both. They are asking for the answer in both minute and second. Minutes and second. Let's proceed. So 1.4 divided by 30, let's multiply 60 in the denominator. That will give me mole per liter per second value. So if you simply calculate it, it will give you some value something like 0.00078 mole per liter per second. So that is the second answer. So I guess you understood this. So yeah, here comes the end of our model paper 1. Model paper 2 videos also will be coming soon. So before that, please make sure that you are practicing enough all the questions, and as I told, which questions are board alert, which particular zone they are actually targeting. I guess you got a little bit idea about it. So in accordance to that, keep practicing and please spice up the things by adding more concepts in your studies. For today, it's this much. In the upcoming video, we will proceed further with the model paper 2. So to get more videos, please subscribe the channel. Thank you so much.